What existed before existence itself? Exploring the paradox of time. Now, those of you who are a bit more advanced might have already guessed where I'm starting from: the singularity. Ever since science definitively established that the universe had a beginning, this concept has become the fundamental starting point for serious thinkers. The worldview completely shifted when scientists realized it had a beginning, an antonym to the word finite. But actually, at first, there was no beginning. At least, that's what science believed a couple of centuries ago. In fact, even at the beginning of the 20th century, physicists still held this view. They imagined the universe stretching infinitely through space and time, existing everywhere and always. This gave them a sense of calm certainty, which to some extent allowed them to overlook certain logical inconsistencies. For instance, what does it mean for the universe to exist forever? Well, it means its lifespan will never expire. In other words, it will never reach its own demise. Simple enough, right? However, this raised a hanging question about the past. How could the universe have always existed? After all, that implies eternity in the past as well. How could such an eternity have elapsed to bring us to the present day? Why do we exist at all if an infinitely impassable duration preceded our existence? Clearly, even theoretically, the universe could only be eternal in one direction, not like a mathematical line extending infinitely in both directions, but rather like a mathematical ray originating from a single point and stretching into infinity. In that scenario, looking back, we could always state that a certain number of billions of years have passed since the world's beginning, while looking forward, we would see eternity ahead. Now, it's true that Christianity had already somewhat devalued this idea. The ancient pagan world, for example, was cyclical. Christianity, however, broke this cycle, severing the circle of time and halting its seemingly meaningless rotation. Time became a directed segment. The world now had a beginning, creation, and an end, the last judgment. On both sides of this segment, an incomprehensible, bottomless eternity stretched out. To the left of this temporal segment, the incorporeal spirit of Elohim hovered, while to the right, throngs of content-righteous souls and sorrowful sinners resided, some in heavenly nirvana, others in fiery Gehenna, experiencing bliss and spiritual torment respectively. When scientific advancements first began to question the existence of the Christian God, positivist scientists proposed that the universe had always existed and would continue to exist forever. This became the first scientific model of the cosmos. However, this model had its drawbacks, both logical and physical. Firstly, if the universe were infinite in all directions, it would contain an infinite number of stars, meaning that every point in the night sky should be occupied by a star. Consequently, the entire night sky should be ablaze with light. Instead of a dark sky with a scattering of stars, there should be a continuous glow. Yet, this is clearly not what we observe. Perhaps the number of stars, while vast, is ultimately finite. Secondly, Albert Einstein pointed out that in an eternal and uniform universe, stars, under the influence of gravity and due to random irregularities, should have long ago coalesced into one massive clump, collapsing upon each other. After all, stars are not arranged in a strictly mathematical, three-dimensional grid. This means there would always be some, even minor, stellar concentrations, which would inevitably act as gravitational attractors, initially causing a weak, then increasingly accelerating movement of other stars towards these clusters, and from there, disaster would not be far off. In other words, a stationary universe is simply unstable, and since it is eternal, it should have collapsed in on itself an eternity ago. So, why didn't this universal catastrophe occur? Perhaps alongside the forces of universal gravitation, there are also forces of repulsion at play? To give the universe equilibrium, Einstein introduced a term into his equations, a cosmological constant, which he denoted with the Greek letter lambda, written as the symbol L. This lambda was meant to provide the repulsive force between stars. Einstein himself disliked his lambda because, as a physicist, he had essentially conjured it out of thin air, simply to balance the terms in his formula, and, at the same time, to save his model of the universe from becoming a cosmic pile-up. Many other physicists also disliked Einstein's lambda for the very same reason. While the forces of universal gravitation were evident, there was absolutely no sign of any universal repulsive forces. The brilliant physicist Lev Landau even forbade his students from mentioning this rotten lambda. So, in essence, physicists needed a different explanation for the universe's existence. This explanation was found in 1923 by the Petersburg professor Alexander Friedman, who proposed a non-stationary solution to Einstein's equations. He demonstrated that if the universe were expanding, then this expansion could successfully replace the lambda term Einstein had invented. The reason star clusters weren't collapsing in on each other due to gravity was that galaxies were actively moving away from one another, as if they had all originated from a single central point after a powerful initial impulse. Later, this was confirmed experimentally. In the 1930s, the American astronomer Edwin Hubble analyzed astronomical observation data. He discovered what is known as redshift, which indicated that galaxies were indeed moving away from Earth, and moreover, the farther away they were, the faster they receded. Additionally, a cosmic background temperature of 3 degrees Kelvin, or negative 270 degrees Celsius, was detected throughout the universe. No matter which direction a radio telescope was pointed, a pervasive noise at a frequency of 3 times 10 to the 11th Hz was detected, with no discernible specific source. This was identified as the universe's thermal noise, the remnants of the immense temperatures that raged during its birth. Today, science broadly describes the birth of the universe in the following way. The cosmos emerged from a singularity. Now, as most curious minds are aware, a singularity is a point of infinitely small radius with infinitely large density and temperature. This point, often referred to as the Big Bang, is believed to have created matter, time, and space itself. This event, according to the latest data, occurred approximately 13.7 billion years ago. But what existed before the singularity, and where did it even come from? Moreover, how could it have appeared if there was no space? These are excellent questions, and they're always posed to physicists, and physicists, in their earnest attempts to answer, often resort to terms like primary vacuum or Higgs boson. Well, after hearing those explanations, people usually don't have more questions. In fact, their desire to ask anything further often just evaporates. So, to avoid such difficulties, perhaps we should start with a response I've given countless times to a very natural initial question. The question itself is incorrectly formulated. The incorrectness here is similar to that in the famous loaded question, have you stopped drinking brandy in the mornings? It's impossible to answer succinctly, because the question already contains an assertion that you drink brandy every morning. And it only asks one thing, have you quit, or are you still doing it? What if I don't drink at all? Or what if it's not brandy, or not in the mornings? Or perhaps only very occasionally. The same applies to the question of what existed before the singularity. You see, the word before implies a scale, a timeline, on which, relative to any arbitrary point, we can designate a state before, or to the left, and a state after, or to the right. But what if this scale isn't a straight line, but rather a ray? A ray has nothing to the left of its starting point. Consequently, the question of what existed before the singularity makes no sense whatsoever, because there simply was no time. So, why do physicists claim there was no time? Well, because there were no events. And please, hear me out. This is a very important point about events. Let's not get carried away with fantasies here. We understand that time, as such, doesn't exist. Time is simply the movement of matter in space, which we perceive as time. I've tried explaining this to Valera, but sometimes people find it incredibly difficult to grasp simple concepts. To travel into the past, all that would be required is for every atom, every radiation, and every elementary particle in the universe to be arranged precisely as they were at the specific moment in time you wish to revisit, in the exact same spatial coordinates and with the identical momenta. Of course, this excludes the molecules and atoms that make up you, since you'd want to arrive in the past as yourself, not transform into an infant or simply vanish. As you can imagine, this is impossible for numerous reasons. There simply isn't enough energy in the universe to rearrange all its particles into the required configuration and then set them in motion, nor is there any mechanism capable of making them do so. Furthermore, we have no idea how all the particles in the universe were arranged, say, on October 25, 1117. And if we then consider Heisenberg's principle, also known as the uncertainty principle, the task becomes utterly unfathomable. Heisenberg's principle states that, fundamentally, we can never simultaneously know both the momentum or speed and the exact position or coordinate of a particle. But we'll delve deeper into Heisenberg's work a little later. Time, you see, is just as much an artificial construct invented by physicists as energy is. After all, energy in itself doesn't truly exist either. Pure energy in its unadulterated form simply isn't found. There's motion, which we perceive as a measure of kinetic energy. There's the height to which a body is lifted, which we perceive as potential energy, and there are electromagnetic radiations, which physicists sometimes do indeed label as energy lifted rate. But this is just a figure of speech, much like saying the kettle boiled. The kettle itself doesn't boil. It's the water inside the kettle that boils. It's just that after Einstein penned his famous formula, E=mc², people began to say that science had established a connection between energy and mass. In reality, Einstein's formula simply made it possible to express any energy in units of mass, like kilograms, and any mass in units of energy, such as joules. That's all it did. However, in a physical sense, the formula established a link between matter and radiation. Radiation isn't energy. Radiation is matter. Matter, in fact, has three primary forms: substance, field, and vacuum. The fictions of energy were simply invented by physicists for the purpose of calculation. So, time is merely a conceptual quantity, a convenient construct for calculations. There is no energy in the world, and there is no time. There is only moving matter. In fact, time has always been measured by uniform motion, by the movement of a clock's hands, by sand flowing through a glass hourglass, or by the Earth's revolutions around the sun. But why is time directional? Indeed, in space you can move right or left, forward or backward. Yet in time, we only move forward. Why does the arrow of time exist? For the very same reason. Time doesn't exist. Time manifests itself through the laws of matter's movement, and these laws dictate that certain processes proceed directionally. This is precisely what we perceive as the direction of time. For example, heat always transfers from a hotter body to a cooler one. Why? Well, purely statistically. You see, heat is a measure of the speed of a body's particles. Hot particles, meaning faster ones, colliding with colder particles, transfer part of their momentum to them, thereby equalizing their speeds. Of course, theoretically, it's possible for a slow particle to strike a fast one so perfectly that the fast particle's speed increases even further, while the slow one comes to a complete halt. However, this is extremely improbable. Such a specific spatial combination of speeds and directions of motion, for instance, a slow atom catching up to a fast one from behind and pushing it at a precise angle, occurs very rarely. Most often, what happens are typical chaotic collisions that ultimately equalize the speeds. So, the famous second law of thermodynamics, which prohibits the transfer of heat from colder bodies to hotter ones, is purely statistical in nature. And the heat death of the universe, as predicted by Clausius, is, in fact, the thermodynamic component of the arrow of time. There are other components as well. When two protons collide, they produce a nucleus of heavy hydrogen, a positron, and a neutrino. This is one of the reactions that occurs within low-mass stars. Theoretically, all reactions in nature are reversible. But after the collision, the neutrino flew away from the star at the speed of light, effectively disappearing without a trace. In theory, one could imagine a heavy hydrogen nucleus, a positron, and a stray neutrino meeting up. However, the probability of such a reunion is, firstly, extremely low. And secondly, neutrinos interact very weakly with matter. This elusive particle, you see, can easily pass through a lead plate the thickness of the distance from the Earth to the Sun. So for this reason as well, the likelihood of a reverse reaction is negligible. That's why stars shine, because they undergo directed, irreversible reactions. The direction of time, in essence, is this irreversibility, which is really just a series of directed reactions. We cannot say what existed before the singularity. But we can certainly talk about what happened afterwards, and we can make some assumptions about how it came into being. Let's imagine time from creation. 0 marks the singularity. Infinite density, infinite temperature, infinitesimally small size, a point. The very starting point. When 10 to the power of minus 35 seconds had passed since the beginning of the universe, the grand unified force ceased to exist. Now, I'll need to explain what exactly the grand unified force is. However, we won't delve too deeply into the intricacies of physics. I'll briefly mention for your information that any event occurring in our world can only be explained by 4 main physical interactions: the strong, the weak, the electromagnetic, and the gravitational. Gravitational interaction is responsible for universal gravitation. For instance, the Earth's orbit around the Sun, and the fact that we walk on our planet instead of floating off into space. Any object possessing mass is attracted to any other massive object. Mass is one of the fundamental properties of matter. Another property of matter is electric charge. While gravitational charge effectively has only one sign, after all all bodies are massive, and all masses attract. There are two types of electric charges, positive and negative. Like charges repel, while opposite charges attract. This phenomenon is known as electromagnetic interaction. Electromagnetic interaction is responsible for almost everything we observe around us, all chemistry, biology, elasticity, and friction forces. Chemical, biological, and mechanical reactions are in fact all various manifestations of electromagnetic interaction. The strong interaction, on the other hand, is intranuclear. Were it not for these remarkable forces, atomic nuclei would instantly fly apart due to electrostatic repulsion, seeing as they are composed of identically charged particles, protons. Finally, we have the weak interaction, also known as beta decay. It is responsible for the transformation of elementary particles in the microcosm. Typically, a neutrino is emitted during weak interactions. It's believed that in the very first instant of the universe's existence, when its size was merely a few microns, all fundamental interactions were unified, forming a single, grand, unified force. Currently, all efforts by physicists are focused on developing a theory that would unify these four interactions into one, namely, the theory of supersymmetry. Such a theory would unify all interactions and, consequently, explain a great deal about our world. However, so far, scientists have only managed to unify two interactions, the electromagnetic and the weak. Let's return to our universe, which at this point was 10 to the power of minus 35 seconds old. The temperature of the universe at that moment was 10 to the power 32 degrees Kelvin, and its density was 10 to the power 92 grams per cubic centimeter. To give you some perspective on what 10 to the power of 32 degrees Kelvin means, let me tell you that it's actually 10 to the power of 27 degrees Kelvin. That is, the universe's temperature at that time was 1, followed by 27 zeros. Whether in Kelvin or Celsius, it makes no difference at that scale. And the age of the universe was 1 divided by 1, followed by 36 zeros of a second. At this point, the diameter of the universe was about 1 centimeter, which is just slightly larger than a tennis ball. It was at this exact moment that the gravitational interaction separated from the grand unified force, thereby increasing the universe's diversity by 1. This marked the very first step in its evolution. But what exactly is evolution anyway? Well, evolution is essentially the process of material systems becoming more complex. Following this, the universe rapidly expanded, exchanging heat as it did so. Later, the renowned physicist Alexander Linde would term this rapid expansion inflation. In the very first moments, there was absolutely no distinction between matter and radiation. They were symmetrical, indistinguishable. Through countless collisions, matter transformed into fields, and fields, in turn, transformed back into matter. Eventually, matter and radiation separated. Then, the strong interaction also separated, bringing the total to 3: gravitational, strong, and electroweak. At the point when the universe was 10 to the power of minus 10 seconds old, the weak interaction finally separated from the electromagnetic. At that time, the universe's density was 10 to the power of 20 to 8 grams per cubic centimeter. Its temperature was 10 to the power of 15 degrees Kelvin, and the diameter of the universe was approaching 1 billion kilometers. Time passed, and when the universe was just 10 to the minus 6th power seconds old, its temperature dropped to truly astonishing levels, specifically 10 to the 12th power degrees Kelvin, or 100 billion degrees. At this point, neutrons and protons began to clump together and form. Now, a small explanation is necessary here. As you might know, virtually all matter we see around us is made up of 3 elementary particles: protons, neutrons, and electrons. Today, physicists who study elementary particles hypothesize that protons and neutrons in turn consist of even smaller particles called quarks. They've even built a new theoretical science, quantum chromodynamics, on this hypothesis. While it's a sound scientific theory, it's virtually impossible to verify it in practice. To break a proton into its constituent quarks, an absolutely unimaginable amount of energy would be required, the kind that was only present during the very first moments of the universe's life. Back then, the energy of the hot universe was sufficient to tear quarks apart from each other, but times have certainly changed. This is a very important point for understanding the mechanisms of evolution, those very mechanisms that operate at all natural levels. Remember the first rule of evolution: as soon as the binding energy between particles becomes higher than the random ambient energy of their surroundings, the first stable structures emerge. The environment simply doesn't have enough strength to destroy them. Consider a stone, for example. Why doesn't it dissolve or crumble? Because the energy of the surrounding air is insufficient to break the bonds within it. But if we were to start increasing the environmental energy, the stone would eventually melt and crumble. Marriage, for instance, is essentially the cohabitation of two human particles. But if we were to start increasing the aggressive energy of the environment, creating unbearable difficulties in people's lives, their marriage would break down. The energy of the environment would then exceed the energy of the marital bond. However, we are still far from talking about marriages. So far, only 10 to the minus 6th seconds have passed in our cosmic timeline. The universe was a chaotic mix of leptons, radiation, protons, and neutrons. As the temperature continued to drop, these material structures became even more complex. When 1/100th of a second had passed since the birth of the world, its temperature fell to 30 billion degrees. At this time, the first helium nuclei, protons, neutrons, and heavy hydrogen nuclei began to form. An important point here: practically all the particles in the nascent universe had already annihilated by this point, transforming into flashes of light. Only a minuscule amount remained, just 1/1000th of what was originally there. This happened because there was 1/1000th more matter particles than antimatter particles, and it is from this single remaining 1/1000th that our entire world is now composed. Truly, just 1/1000th of what once existed. I bring this up so that you understand the second evolutionary rule. The number of unsuccessful attempts vastly exceeds the number of successful ones. Nature operates without a plan. It acts blindly, through trial and error. Therefore, it has to work with a huge surplus. For example, to create our world, it needed 1 billion times more material than was ultimately necessary. And immediately, we come to the third rule of evolution. Over time, the number of successful attempts increases. Out of millions of dandelion seeds, only 1 or 2 survive. From 1,105,000 oyster larvae, just 1 makes it to maturity. That's why, to continue its species, an oyster lays 150 million eggs. These are astronomical numbers, aren't they? However, as the level of matter's organization increases, the number of successful attempts rises. For a dozen sturgeon fry to survive, nature needs millions of eggs. A century ago, in peasant families, up to half of the children born might not survive. Today, for modern city dwellers, almost all children survive. These are clear examples of evolution in action, and we will return to this phenomenon many times again. So, 300,000 years had passed. The universe had expanded even further. Its temperature had dropped to 30,000 degrees, and the appearance of the first atoms became possible. The thing is, the binding energy of an electron to an atomic nucleus is 13.6 electron volts, and as soon as the ambient energy dropped below this threshold, electrons stopped being torn away from the nucleus. 200 million years went by. The universe's temperature had fallen to approximately 300 degrees Kelvin. More complex structures began to form, namely stars. They condensed from hydrogen with an admixture of helium. Just a few years ago, it was thought that the first stars ignited only 1 billion years after the world began. However, the latest astronomical data has reduced that time frame by a factor of 5. Further evolution of matter then proceeded within the stellar furnaces. Everything found in the periodic table of chemical elements to the right of and below helium, essentially almost the entire Mendeleev periodic table, is a product of these stellar nuclear fusion factories, the specific reactions of which I won't detail now. Within the cores of the first generation of stars, the matter that constitutes you and me was produced. All that carbon, magnesium, oxygen, and iron. In short, everything except transuranic elements. Elements located in the periodic table to the right of iron are generated during supernova explosions. Depending on its mass, a star can either quietly fade away or explode. Some stars did explode, scattering their processed material throughout the galaxy. These elements, scattered as interstellar dust, then condensed under the influence of gravity, eventually forming us. So, one of the astronomers was absolutely right when they said that humans are made of the ashes of dead stars. This isn't just a poetic phrase, it's a simple statement of fact. The process of star formation and stellar burning is, in fact, quite fascinating. I'll just mention that the evolution of matter in interstellar space actually leads to the formation of organic compounds. This means that organic substances first appear not on planets, as many people believe, but directly within interstellar dust. For instance, at the Kitt Peak Observatory in Arizona, there's a millimeter-wave radio telescope specifically designed to search for molecular compounds in interstellar gas. Using this telescope, scientists discovered that the Orion Nebula is what's known as a GMC, a giant molecular cloud. What's more, this cloud contains complex organic compounds such as methylformaldehyde, isocyanic acid, formic acid, methanol, methylamine, dimethyl ether, and many others. And interestingly enough, many of these organic molecules form the very basis of the DNA molecule. These are all examples of the physical and chemical evolution of matter. We haven't yet, however, delved into chemical evolution, followed by biological and indeed social evolution. Did the universe really emerge from nothing? Just like that? A void that isn't empty? Well, yes, it's true. That is, if you consider nothing to be the primordial, eventless vacuum from which the singularity, the very seed of the universe, emerged. But then again, the vacuum is far from nothing at all. It's not an empty void, as many might believe. Ever since Dirac famously called the vacuum a sea of virtual particles, physicists' understanding of it has fundamentally changed. Previously, it was simply seen as an empty container for things. But now, in the minds of scientists, it has transformed into a full-fledged form of matter, albeit with some rather unusual properties. The vacuum, you see, is an ocean of virtual particles. That is, particles that are not manifested in any way. These are particles with no discernible properties, particles existing in a peculiar zero state. Now, visualizing this isn't easy. After all, if something doesn't manifest itself in this world, it logically means it doesn't exist. So why then do physicists speak of the vacuum as a sea of virtual particles? Why not a sea of stools, or of watermelons for that matter? After all, vacuum stools and vacuum watermelons also don't manifest themselves in this world, do they? Well, the thing is, the vacuum is constantly boiling or foaming with activity. Virtual particles continuously pop into reality for a fleeting moment. That is, they appear from nothing and then instantly vanish. Due to the law of conservation of charge, particles emerge from the vacuum only in pairs, a particle alongside its antiparticle. For example, an electron and a positron, or a proton and an antiproton. These pairs emerge and immediately annihilate each other. They annihilate so rapidly that it's impossible to observe them directly. However, it is possible to separate them. If a strong electromagnetic field is applied to the vacuum, one can actually pull apart the newly formed electron and positron in opposite directions. Such experiments have indeed been successfully conducted. Yet another effect has been discovered, one that further demonstrates how the vacuum continuously creates and devours particles. Physicists reasoned that if the vacuum truly boils with activity, then the electron-positron pairs forming around a real atom should introduce subtle corrections to the electron's motion, and, in effect, shield the electron's charge from an external observer. These precise effects were indeed experimentally observed and are known as the Lamb shift. Towards the very end of the 20th century, a conference on science and faith took place in Berkeley, California. More than 300 leading figures in physics and biology from around the world gathered there, the majority of whom were, in fact, believers. One of the participants, Charles Townes, who in 1964, along with Basov and Prokhorov, received the Nobel Prize for the creation of the laser and maser, made a remarkable statement. An intelligent being is hidden in the laws of nature. Now one might think, well, he said it, so what? People say all sorts of things. However, within the broader context of that conference, his statement resonated so profoundly that even a serious journal like Science came out with the headline, "Science Discovers God." Of course, Science was rather hasty with that headline. Firstly, the majority of scientists are, after all, non-believers. The journal Nature, for instance, published survey data among American scientists. It revealed that even in puritanical, God-fearing America, for a scientist to openly admit belief in God is considered politically incorrect, impolite, tantamount to publicly confessing to incest, in fact. It's even seen as suspicious. Only just over 40% of scientists admitted to believing in a personal God. Now pay attention to that phrasing, a personal God. It's a rather vague formulation, almost a euphemism for the word agnostic. In other words, Americans who doubt God's existence are often reluctant to label themselves with the seemingly undesirable word, atheist. Secondly, science in fact cannot discover God. Rather, it continually closes off the idea of God. Even genuinely religious physicists resolutely exclude God from their respective domains. physicists from physics, and biologists from biology. This is because scientists seek natural explanations for reality, not supernatural ones. No scientist uses the hypothesis of God in their research, because to employ such a hypothesis would simply mean to stop thinking and start praying. Incidentally, the Vatican observed the aforementioned conference with considerable interest. They sought to reconcile faith with science. This is despite the fact that individual scientists resolutely push God beyond the boundaries of their knowledge, relegating him either to the realm of the unknown or to the ephemeral domain of the spirit. Pope John Paul II, for his part, generally held a very lenient attitude toward science. He rehabilitated Galileo and apologized for the minor inconveniences inflicted upon Europe by the Holy Inquisition. Furthermore, in his 1998 encyclical, he even proposed that scientists and the Church declare a truce. The Vatican no longer protests against the origin of man from apes. In fact, having overcome resistance from the most reactionary wing of the clergy, it recognized and blessed Darwin's theory of evolution, stating, "Let's not argue. Biologists understand this better anyway." Essentially, only one area of science remained for the Pope, behind which God could still potentially hide: cosmogony. It's quite a paradox. The very cosmogony that once caused friction between the Church and science, with the acceptance of the Big Bang, actually breathed new life into the once disheartened Church. The recognition of the Big Bang, exclaimed Vatican astronomer Jesuit Father William Stegen, only ennobled the image of God. Indeed, if the world had a beginning, if there was a primeval impulse, then God very conveniently re-emerged as the first cause. Who provided this initial impulse? Who created the singularity? And why couldn't that be God? It's interesting to note that one of the creators of the Big Bang theory was the Belgian priest and astronomer Georges Lemaitre. In 1931, he published a theory proposing that the universe originated from a primeval atom that exploded, giving rise to time, space, and matter. The evolution of the universe, Lemaitre wrote, is like a firework display, and we are now watching the last embers of its cooled lava slowly dying out. He conceived this theory in the late 1920s after visiting the Mount Wilson Observatory in California. It was there that Edwin Hubble observed galaxies receding from each other, much like fragments from an exploding grenade. The Big Bang theory led to two main hypotheses regarding the universe's ultimate fate. Either the expansion of galaxies would eventually halt, slowed by the force of universal gravitation, or it would continue indefinitely. In the first scenario, the galaxies would stop, and then begin an accelerating collapse back into a singularity. Nothing could possibly survive this cosmic nightmare. As we know, a singularity is a state where there is no time, no space, not even elementary particles. However, this singularity could then potentially explode again, forming a new universe. In the second scenario, the galaxies would continue to expand forever. Eventually, stars would burn out, leaving behind cold lumps of matter, such as dead stars and planets, adrift in a dark, vast space. There's also an even more unsettling possibility. The very fabric of matter could decay. This hinges on whether the proton is truly eternal. Historically, protons were thought to be stable, everlasting particles. However, theoretical physicists later began to hypothesize that while their lifespan is incredibly long, it might not be infinite. Experiments were even conducted, with scientists searching for instances of spontaneous proton decay, but none were found. So, either the proton is indeed eternal, or its lifespan is simply far greater than currently estimated. If protons are not eternal, then all matter in the universe, every cold, cooled lump of it, would eventually decay over countless billions of years. What would be left is only radiation, neutrinos, and a few scattered electrons and positrons. And each particle would be separated from the next by distances billions of times greater than the size of today's observable universe. Imagine the nightmare of an empty eternity, completely devoid of any structure. But the specifics of whether protons decay or not aren't the main point here. The crucial aspect is this: if the universe follows the first pulsating scenario, expanding then collapsing again, then God, as a creator, becomes arguably unnecessary. The universe, or rather universes, would exist self-sufficiently, needing nothing beyond themselves. However, in the second case, that of infinite expansion, it seems to imply a need for something. So, what determines which scenario the universe will follow? Calculations suggest it depends on the universe's average density. If this density is above a critical value, it means the total mass within the universe is sufficient for its gravitational pull to eventually halt the expansion, leading to the galaxies collapsing back together. If the average density is lower, then the expansion will continue indefinitely. The precise value of the universe's average density remains unknown. However, recent data gathered during the final years of the 20th century and the early years of the 21st century has shed new light on the ultimate fate of the cosmos. These findings indicate that the expansion of galaxies will never reverse into a contraction, yet this expansion won't be eternal either. So, in other words, if the universe isn't simply pulsating from one singularity to another, it appears to be eternal in one direction, towards the future. But, then, the new Hubble Space Telescope made its contribution. The Hubble Space Telescope cost Americans $1.5 billion. When it was launched into space in 1990, it became the most expensive satellite in human history. However, that wasn't enough. An expedition of 7 astronauts had to be sent on a space shuttle because the telescope's optics were found to be insufficient for the observation scientists hoped to achieve. Refitting the telescope in orbit cost another $1 billion. So, what exactly did humanity gain for $2.5 billion US? Well, new knowledge about the beginning and end of the universe. For one, the telescope managed to peer 12 billion years into the past, helping us understand something crucial about the universe's origins. After all, telescopes are, in essence, time machines. The more sensitive they are, the further they can look into space and, consequently, back in time. Light from the moon takes 1 second to reach Earth, while light from the sun takes 8 minutes. So, we see the moon as it was 1 second ago. We see the sun as it was 8 minutes ago. We see the star Alpha Centauri as it was 4.3 years ago, because it is 4.3 light years away. Hubble peered back 12 billion years, whether you consider those light years or simply regular years. With further advances, we'll undoubtedly look even further, getting closer still to the very first moments of creation. Hubble focused its studies on supernovae. Supernovae, as you might know, are exploding stars, and their study yielded a sensational discovery. The rate of expansion of galaxies in the universe is actually accelerating rather than slowing down. This was extremely strange, because gravity should naturally be slowing down the initial impulse from the Big Bang. The fact that they aren't decelerating but instead accelerating was completely unexpected for astronomers. It turns out some mysterious force is powerfully pushing the universe apart. Space itself, essentially a vacuum, is expanding like dough rising, carrying the raisins of galaxies within it further and further apart from one another. So what exactly is acting as the catalyst here? What accounts for 70% of the universe's total energy? Well, it's attributed to this mysterious repulsive force, one that seems to emerge from emptiness, from nothingness, from the vacuum itself. Could it be that God is, in fact, nothingness? Let's recall the elusive Einsteinian cosmological constant of cosmic repulsion. Nowadays, both physicists and journalists refer to it as dark energy. This term has, in fact, become well established. However, while journalists often perceive dark energy as something almost mystical, physicists are actively searching for its material essence. Previously, it was simply taken for granted that the density of empty space was 0. The density of water, for example, is 1, meaning that 1 cubic centimeter of water contains 1 gram of the substance. Similarly, 1 cc of iron contains around 8 grams of matter. In empty space, however, there was thought to be none at all, 0 grams. Therefore, it was assumed that the density of a vacuum must be 0. But here's the thing. A vacuum is not empty space. Instead, it's considered a sea of unmanifested particles. Furthermore, a vacuum always contains some electromagnetic field. So, here's one scenario for the universe's future. Taking into account this vacuum repulsion, it was developed by Professor Robert Caldwell from the California Institute of Technology. His work resulted in what's known as the Big Rip theory, which postulates that in 22 billion years, dark energy will completely tear the universe into elementary particles. Initially, the universe is thought to be on a plateau, but then, this process will intensify, taking an accelerating and explosive path. Galaxies will break apart into individual stars. A month before the Big Rip, the planets will be flung away from the sun, scattering in all directions. Also, a month before this ultimate end, the gaseous spheres of stars will begin to fly apart. Then, just 30 minutes before the end, planets will start exploding. Dan, A mere few seconds before the final collapse, atoms will be torn apart. Then, at 10 to the power of minus 19 seconds before the ultimate end, electrons will be ripped from their atomic orbits, and shortly after that, atomic nuclei will disintegrate, scattering into individual protons and neutrons. The universe will once again become lifeless and empty. This rather bleak scenario will only come to pass if, firstly, Caldwell is correct in his calculations and assumptions, and secondly, if the astronomical observations of supernovae have been interpreted accurately. Meanwhile, the world-renowned physicist Alexander Linde, the very same Linde who once lived in St. Petersburg and now serves as a professor at Stanford, doesn't believe the universe faces an eternal scattering. Instead, he believes we are currently witnessing the final phase of its expansion, which will eventually be followed by contraction. But in any case, all of this is still a long way off. We'll delve into the future of humanity and the world in a later discussion. But for now, let's turn our attention to the concept of a physical God. Having gotten a bit carried away with discussions about the end of the universe, we've momentarily forgotten about God, and indeed, the main question: where did the singularity actually come from? Well, it's finally time to address that. Perhaps a divine hand brought it about? It's worth noting that the understanding of God among the latest wave of religious physicists and cosmologists differs quite significantly from traditional views. They simply know too much about the universe for their God to resemble the God of yesteryear. A new kind of God, you see, has emerged, one who is neither an omnipotent ruler, nor a global controller, nor a judge. This God, it seems, cares little for the tiny specks of life scurrying on one of the planets, orbiting a rather third-rate yellow dwarf on the outskirts of one of myriad galaxies. Over the past 13 billion years, no trace of involvement in the universe's affairs has been observed. This is a God who, perhaps, once set the universe in motion, but no longer intervenes in the course of its events. It's not just physicists, but also modern biologists, who are, of course, intimately familiar with evolution, who assign God a rather modest role, that of a brilliant design engineer. They know, you see, that the laws of nature are entirely sufficient for the development of the universe and humanity within it. Nobel laureate and geneticist Werner Arber, for example, once remarked, God created something self-organizing. He was so clever, in fact, that he planned everything in such a way that there was absolutely no need for him to intervene. So, in this view, God isn't needed. Everything simply proceeds in its own course, which was, in fact, set by him once and for all. But was it really him? We'll get to that crucial question very soon. However, even if God did indeed set the universe in motion, he couldn't possibly have foreseen how everything would unfold within it. This is because, in creating the laws of the universe, he himself in a way created the famous uncertainty principle, otherwise known as Heisenberg's principle. This principle, of course, underpins all universal randomness and fundamental unpredictability. We'll discuss this principle in more detail later. For now, however, let's just note that, having been discovered in the early 20th century, it effectively put an end to the legends of divine omniscience. Its discovery, in fact, shook even the physicists of that era, many of whom had grown up entirely within the paradigm of Newtonian mechanics. Even Einstein himself famously wondered, does God play dice? Now, this doesn't mean Einstein actually believed in God. In 1921, Einstein received a telegram from New York Rabbi Herbert Goldstein that simply asked, "Do you believe in God?" Prepaid reply, 50 words. Einstein in turn managed to respond in just 24 words. He wrote, "I believe in Spinoza's God, who reveals himself in the orderly harmony of what exists, but not in a God who concerns himself with the fates and actions of human beings." For Einstein, then, God was simply nature itself. The 17th century thinker mentioned by Einstein who first identified God with nature was, predictably, not accepted by the church. In their view, God simply seemed too insignificant. So, what then remains of religion, and more importantly, of the institution of the church, if God is stripped of the ability to decide who is favored, or conversely, disfavored? Modern physicists have, in fact, gone beyond Spinoza and Einstein. One of the Big Bang theorists, Steven Weinberg, reasoned this way: if God has become inert, frozen beyond space and time, if God distances himself from everything, allowing science to explore the world, then why not simply abandon the concept of such a God altogether? Science has already expelled God from nearly every corner of the universe, leaving only a faint, barely discernible shadow at its very origins. Is it really necessary to continue this hypocrisy? To involve something in our universe that has never actually been within it, and has never truly existed anywhere? After all, attributing a personified will to the impersonal laws of nature is, quite frankly, pure hypocrisy. Well, you certainly can't deny Weinberg's consistency and logic. He is, in fact, supported by Nobel laureate Leon Lederman, who stated, "On the cutting edge of science, there's still a corner where a creator might reside, but over the past half-century, that corner has noticeably shrunk." It's almost as if St. Augustine had a crystal ball. More than 1,500 years ago, he predicted that the efforts of scientists would not bode well for the concept of God, saying, "These stubborn, learned, and pedantic individuals will not rest until they have expelled the Creator from the entire universe." Until quite recently, there was only one remaining task for God in the world: to create the universe by forming a singularity. Otherwise, where did it come from? However, even in this domain, God has suffered a crushing defeat in recent decades. Physicists have devised a way for a singularity to emerge from absolutely nothing. It all comes down to the concept of the primordial vacuum and quantum mechanics. If a vacuum can generate matter, for example, electron-positron pairs, then why couldn't the vacuum fluctuation give birth to tiny universes? The Russian physicist Igor Novikov and the renowned American physicist Stephen Hawking, who, as you may know, was a paralyzed individual who communicated using a specialized electronic device that generated speech directly from his larynx. Well, their calculations demonstrated the fundamental possibility of such a hypothesis. Everything, in essence, arose from nothing. What's particularly interesting is that this doesn't contradict any fundamental physical laws of conservation. This is because the positive energy of the universe's matter can actually be compensated for by the negative energy of gravity. As a result, the total energy of the universe is equal to zero. The universe's total electrical charge is also zero. It is, on the whole, electrically neutral. But what about the significant baryon charge and the lepton charge? Well, both theory and practical observation indicate that there is no strict requirement for the conservation of these specific charges at ultra-high temperatures. So, it seems our universe is the child of a fluctuation, a global, unpredictable randomness. However, Stephen Hawking was quick to reassure religious leaders with a smile, saying this doesn't prove God doesn't exist at all. Rather, it simply means there's no necessity for God. However, religious leaders still had one last ace up their sleeve, one final line of defense: the set of unique, universal constants. Our world is in some ways truly astonishing. It appears almost intentionally designed, as if its very purpose was to foster humanity, or more broadly speaking, complex structures. For example, a proton is 1,836 times heavier than an electron. Why precisely 1836? Why not 342? Or just 1, or perhaps 28,546? Theory doesn't dictate that the mass ratio of a proton to an electron should be exactly 1836. Yet, if it were even slightly different, no complex systems, no molecules, not even atoms, could exist in such a universe. Furthermore, if the electron's mass were just slightly higher, say by only 0.1% of the hydrogen atom's mass, the lifespan of stars would drastically shorten, and evolution simply wouldn't have enough time to give rise to life. If the binding energy within the nucleus were lower, the synthesis of nuclei in stars would not be possible. The universal gravitational constant, which we all learned about in school while studying Newton's law of universal gravitation, is equal to 6.672 times 10 to the power of minus 11, not, for instance, 6.84 or even 5. If this constant were just a little bit larger, the universe would have long ago collapsed back into a singularity. And the real problem here is that physicists see no underlying reason why the gravitational constant should have this precise value. The same applies to the values of particle charges, the speed of light, and the strengths of nuclear forces. Today we know of dozens of various constants and the relationships between them. What's truly astonishing is that all of them are critically important for the existence of our world, yet none of them can be derived from any existing theories. It's almost as if someone intentionally selected these specific values for the universal constants to create the conditions necessary for life to emerge in our world. This particular circumstance naturally brings great joy to theologians, and they speak with triumphant smiles about divine providence. Indeed, the probability of these physical constants having arisen randomly is so incredibly low that one can't help but wonder if they were, in fact, intentionally set to these precise values. The British physicist Paul Davies once remarked, "If we could redesign the universe, we would find that life could not have emerged in any of the universes we created. It could only emerge with the unique combination of physical parameters that we possess. This gives rise to the feeling that the universe was specifically crafted for humans." This paradox became known as the anthropic principle, which of course soon received a successful natural explanation. In fact, two explanations to choose from. The first explanation is this. Physicists genuinely don't see any inherent reason why physical constants should have precisely their current values, and no others. Frankly, they don't even fully grasp the underlying physical nature of many of these constants. For instance, what exactly is baryonic charge? What is electric charge? And what about mass? Why does an electron have one specific mass and a proton another? For the average person, electric charge is somewhat more understandable than baryonic charge. Mass is even more intuitive as everyone uses scales at the market or grocery store. Many people even diet attempting to reduce their body mass. So people are accustomed to mass, and I would argue that this familiarity often creates an illusion of understanding. In most cases, familiarity represents merely a superficial level of understanding. But for physicists, a first approximation isn't enough. They need to delve into the true essence of things. Physicists understand that, fundamentally, elasticity or friction, for example, are merely manifestations of electromagnetism. Friction, chemistry, elasticity, plasticity, biology, all of these are just different expressions of the attraction between a charged electron and a positively charged proton. This attraction forms the foundation of everything we observe around us, the very basis of our own existence, of love, of hatred, of civilization, and indeed of all matter. Electric charge is what builds matter. But what, at its core, is charge? As of now, there's no answer to this question. Of course, a unified field theory, sometimes called the theory of everything, will eventually emerge, and that theory will provide the answer. Perhaps this theory will clarify the physical meaning and intrinsic nature of charges, spin, strangeness, color charge, and other quantum properties. It might also reveal the mechanism that fixes universal constants, such as the speed of light, Planck's constant, the gravitational constant, and so on and so forth. Those constants that define the very character of our world. Now for the second explanation, which is even simpler. Indeed, if the vacuum boils with quantum fluctuations, and one of these fluctuations expanded to the scale of our entire universe, then why really should there be only one universe? That would seem rather odd, wouldn't it? There should be myriads of universes. The cosmos, in this view, would simply teem with universes, much like boiling soup bubbles. This theory was proposed by physicists, including Lee Smolin and Steven Weinberg. In each of these infinite universes, there would be its own unique set of physical constants. It's simply that, in those universes where the physical constants are different, the emergence of complex structures would be impossible. Consequently, there would be no one there to ponder divine providence. And that, in essence, is the whole explanation for our perceived uniqueness. In other words, out of an infinite number of universes, there's a small percentage where life can emerge, even if there are dozens or even hundreds of physical constants and their possible variations. If we imagine shaking a box and we have an infinite number of attempts, then every millionth or trillionth shake will, by chance, produce the right combination. This illustrates, once again, the law of evolution. Nature operates by trial and error. Out of 1 trillion attempts to create universes, one succeeds. Only 1 in a billion particles survives in a nascent universe. To give you some context, only 0.0001% of sturgeon fry survive, whereas more than half of lion cubs, by contrast, make it. So, as evolution progresses, nature becomes more adept. Speaking of evolution, by the way, Professor Lee Smolin of the University of Pennsylvania devised a truly fascinating theory. He directly applied the principle of biological evolution to universes themselves. Before Darwin, people were astonished by how remarkably well adapted all animals seemed to be for life in their natural environments. An anteater, for example, has a long snout and a long tongue specifically designed to extract food from ant colonies. Fish, of course, breathe very effectively with gills, and so on. People would ponder, who could have arranged all of this so intelligently? It must be God. Darwin, however, demonstrated how such intelligent design could arise without any divine intervention, asserting that there was no more inherent intelligence in it than in a stone rolling down a hill. Darwin was, in essence, the Newton of biology. In his time, genes and mutations had not yet been discovered, so he couldn't pinpoint the exact cause of changes in organisms. However, he accurately predicted that random changes in animals must somehow occur from generation to generation, and that out of millions of offspring born, only a select few would survive. Smolin proposed applying this very same principle to universes. According to him, universes undergo selection because, firstly, they reproduce, and secondly, among those that reproduce, only the ones whose descendants do not differ significantly from their ancestors survive and produce further offspring. Smolin hypothesized that universes reproduce through the mechanism of black holes. For the benefit of those who might be less familiar, let me remind you, a black hole is a massive defunct star that has completed its life cycle and undergone gravitational collapse. In some stars, this gravitational compression even reaches what is called the neutron stage. The star transforms into a small object, just a few tens of kilometers in diameter, composed entirely of neutrons. The immense gravity within such a star forces electrons into protons, resulting in electrically neutral neutrons. Now, neutrons are actually unstable. The half-life of a free neutron is about 16 minutes, but within the incredibly dense confines of a neutron star, they simply cannot decay. The body of a neutron star has the density of nuclear matter, essentially forming one gigantic atomic nucleus. A single pinhead-sized amount of this substance would weigh millions of tons. Inside a neutron star, the forces of gravity are balanced by the strong interaction forces between the neutrons themselves. However, if a star's mass is even greater, nothing can halt its collapse. The star implodes, collapsing into a single point. At a certain moment in this collapse, gravity becomes so immense that not even light can escape the star's grasp. Everything can fall into such a star, but nothing can radiate out. Nothing can be observed by an external viewer from what appears as a black hole in space. That critical radius, beyond which nothing can escape the star's pull once it is collapsed, and after which it effectively transforms into a black hole, is known as the event horizon. In physics, this rather evocative term, the event horizon, refers to the boundary beyond which light cannot reach us. And since electromagnetic radiation is the fastest thing that exists in the world, it follows that we cannot receive any information from beyond the event horizon. After all, information isn't some ethereal concept. Information is in fact matter, organized in a specific way, for instance, a radio wave. So, if even radiation cannot reach us from beyond the event horizon, it means no information, no data whatsoever can be obtained from there, simply because there's no way for it to be delivered. For an external observer, the star's collapse will appear to slow down more and more as it approaches the horizon. However, from the star's own perspective, the collapse happens almost instantaneously. This is an effect of the theory of relativity. Gravity slows down the passage of time. So the star implodes into a single point. We know what such a point of infinite pressure is called, a singularity. Smolin, for example, proposed that black holes are the seeds of new universes. Once they pass beyond our event horizon, they contract into a singularity, which then explodes into another universe in a different space. Or rather, not in a different space, but in its own unique space. This new universe creates its own time and space, completely without interfering with our own universe. And, really, how could it interfere from beyond its event horizon? For the star itself, this happens in an instant. From the perspective of our universe, this will never happen. Or more accurately, it will take an eternity to happen. The set of physical constants in a newly born universe can be arbitrary. But if these constants are such that not even atoms can form within it, then stars in such a universe will not ignite, and consequently, there will be no black holes. This means such a universe would be barren. It would not perpetuate the lineage of universes. However, universes with a suitable set of values will proliferate, because stars burn brightly within them, which means black holes are formed from them, and, incidentally, life emerges on planets orbiting these stars. The role of biological mutations in universes is played by the alteration of physical constants. This, then, is a form of cosmic natural selection. Overall, the theory of multiple universes is quite elegant. However, it does have one significant but. This but was quite clearly articulated by one astronomer, who stated, and I quote, "The hypothesis of multiple universes is rather speculative. We might as well have attributed the creation of the world to God Almighty. In both scenarios, in our attempt to unravel the mystery of the cosmos, we find ourselves standing around in a hallway that has nothing to do with serious science.
End quote. What exactly did he mean by that? Well, it means that in this instance, science has essentially concocted a hypothesis that is fundamentally untestable.
Up until now, science's most potent argument against the Church was this: the hypothesis of God is fundamentally untestable, unprovable, and religious scholars would often agree, saying, yes indeed, it cannot be proven, it must be accepted on faith. If you wish to, you accept it, if not, you don't. Yet now, physicists and astronomers themselves have put forward an untestable hypothesis. Since all other universes lie beyond our event horizon, we simply cannot know if they actually exist, or if they are merely our own bare invention. After all, these other universes exist outside our own time and space, because time, space, and the matter moving within them are what constitute a universe. And so, other universes are separated from us by an abyss of non-existence. However, science does have its own joker card, so to speak. This was suggested by none other than Gödel, the mathematician. We'll delve into his truly great theorem later on, but for now, let's just quickly say that if proving a certain proposition within an existing theory is impossible, then one must step outside the confines of that theory. Emptiness and uncertainty govern the world. This is because last century's physics demonstrated that there's no such thing as predetermination, that truth is often contradictory, that objective reality sometimes diverges from common sense, and that a perfect outcome for everyone will simply never exist, anywhere, not even in paradise. So, physics has bestowed upon philosophy quite a few new principles. That's not a bad start for a popular explanation. Let's try again, making it simpler and more accessible. The world our ancestors inhabited just 100 years ago and the world of today are two entirely different realms. Over the past century, civilization's understanding of the world has changed so dramatically that it's difficult to even imagine. But we will try. There's a curious phenomenon that has been observed. The latest principles discovered by science gradually take hold among the masses and even permeate everyday life and human relationships. What was once new and therefore little known gradually becomes common knowledge, commonplace, even trite. Well, who doesn't know that? It becomes part of folklore, and then eventually moves into the realm of superstition, with people saying, for example, "Oh my dear, that's completely outdated, we have new views these days." The Earth, once thought to rest on 3 great whales, first became round. Yet, as the center of the universe, the sun, stars, and planets continued to revolve around it. Then came a changing of the guard, so to speak. The Earth began to orbit the sun, which then assumed the status of the center of the world. Subsequently, even the sun was demoted to a yellow dwarf star and moved from the center of the world to a provincial edge of the galaxy. Now, virtually everyone knows that the Earth isn't flat and that it revolves around the sun. This is a small illustration of how astronomical knowledge permeates broad segments of the population. Similarly, terms like subconscious and libido, originating from psychoanalytic theory, have also permeated the general public, largely thanks to Hollywood films. Barely a century has passed, and everyone it seems uses these terms casually, and often inappropriately. Likewise, people sometimes misuse the phrase about genes, saying, "Oh, that's just in their genes." Typically what they're referring to are traits that aren't inherited at all, for instance laziness or the enigmatic Russian concept of sobornost. It's simply modern folklore. Biologists shouldn't get too worked up about it, and as for the widely distorted theory of relativity, attributed to old man Einstein, well, I don't even want to get started. You often hear, "Everything's relative, old chap." The world is slowly changing, becoming increasingly relative, a shift influenced by the theory of relativity as it permeates wider society. Hold on a moment. The world is indeed becoming increasingly relative. This is a crucial observation, one we really need to chew on, fully digest, and truly take to heart. And that's exactly what we're going to do. Galileo was the first to really challenge the notion of the absolute. He was the first to dismantle the absolute nature of uniform motion. He quite boldly shattered that long-held belief. Before him, it was widely believed that if you didn't continuously apply force to an object, it would eventually stop. But Galileo showed this simply wasn't true. Uniform rectilinear motion, from a physics perspective, turns out to be indistinguishable from a state of rest. It all comes down to the frame of reference, you see. There will always be a coordinate system relative to which a uniformly and rectilinearly moving body can be considered at rest. And indeed it will be at rest relative to that system. Imagine a person sitting in a train carriage. The train is moving at, let's say, 40 kilometers per hour. So, one might ask, at what speed is the person moving? Well, anyone who attended a modern school knows that this question is improperly phrased because it doesn't specify the frame of reference against which we're measuring the person's speed. If measured relative to the train, the person's speed is 0 because they're sitting still. But if measured relative to the Earth, it's 40 kilometers per hour. And if you consider the sun or the moon, it's impossible to determine that speed from the problem's given conditions. But at what speed is the person moving, in reality? Since this is a simple problem, everyone knows that this question itself is meaningless. There's no single true state of motion, and both answers, 0 and 40, are equally valid. However, in more complex scenarios, this apparent obviousness doesn't always seem so clear-cut. Pardon the pun. The next significant blow to the absolute came from Maxwell and the entire group of physicists who were delving into electromagnetism. As they enthusiastically explored this new field of electricity, physicists suddenly found themselves confronted with the fact that electrodynamics was in clear contradiction with the well-established and familiar principles of mechanics. Even as far back as 1837, when Europe was still recovering from the Napoleonic Wars, the great Gauss, the very same whose distribution we'll study later, noted that the forces acting on uniformly moving charges, it turns out, depend on the observer's viewpoint. That is to say, they depend on the coordinate system in which the observer is located, and depending on a change in perspective, these forces could even reverse direction. For instance, like-charged moving particles should repel each other, yet if these same moving charges were viewed differently, as elementary currents, then conductors carrying currents in the same direction should actually attract. So, what was happening in actual fact? For the entire 19th century, the brightest minds grappled with this contradiction, but they failed to resolve it until Einstein arrived on the scene. The general public, far removed from the intricacies of electromagnetism, paid little attention to these electrical experiments. They were content with the electric light bulb and the emergence of the tram, happily leaving physicists to ponder questions like, does it truly exist or not? Public opinion and newspaper journalists, however, could not ignore it. Indeed, it was Einstein who delivered the final, decisive blow to the absolute. All the popular newspapers of the early 20th century were abuzz with talk of the theory of relativity, precisely because it flew in the face of common sense. Two events, let's call them Event A and Event B, might happen either simultaneously or not. What's more, this non-simultaneity itself depended on the frame of reference. In one system, Event A might occur before Event B, while in another, the reverse would be true, with Event B happening first. What's more, the dimensions of objects, their mass, and the very passage of time itself all turned out to depend on the viewpoint, the chosen frame of reference, and the velocity of one coordinate system relative to another. And Einstein's theory wasn't even the final blow to common sense. That's because, following the theory of relativity, quantum mechanics emerged, dealing with magnitudes that were utterly unimaginable. Common sense, too, turned out to be relative. It only worked in the macroscopic world, at low velocities and weak gravitational fields. It was simply the logic of solid objects, a generalization of experience accumulated under terrestrial conditions. Under non-terrestrial conditions, however, experiments yielded different, unfamiliar results, which naturally provoked rejection and seemed to contradict common sense. Pardon me, it didn't just seem to, it absolutely did contradict common sense. You see, common sense has a very limited scope of application. Alas, just like any function. After Einstein, relativity quite literally became a byword. It permeated from science into everyday discourse, into morality, and even into economics. Whereas gold was once considered the absolute measure of value in economic relations, it has now lost that role. Today, money no longer has a gold standard as it once did. Instead, the value or the exchange rate of one currency is determined relative to other world currencies, which together form a single global network. Waves periodically ripple through this network, and depending on which frame of reference, or currency, in this case, you choose, these waves will appear larger or smaller to you, or even completely imperceptible. In short, since the early 20th century, humanity has gradually grown accustomed to the relativity of its perceptions of the world, coming to understand that the world's picture, indeed truth itself, depends on the coordinate system, on one's viewpoint. By the mid to late century, this relativity had even permeated into politics in the form of pluralism and tolerance. The great Austrian mathematician, Kurt Gödel, proved his incompleteness theorem in 1931. Strictly speaking, in mathematical terms, it states, under certain conditions regarding a fundamental pair T, there exists no deductive system PPD over L that is simultaneously complete and consistent with respect to T. Well, it's quite a mouthful, isn't it? To make it a bit clearer, we can rephrase it this way. In any language, there are true statements that cannot be proven. And if we want to put it in truly simple terms, using what you might call plain, direct language, it means this. Within the framework of any theory, all existing statements are built upon unprovable assumptions, known as axioms. And from these axioms, all other statements are then elaborately constructed. To prove these axioms, one would need to step outside their conceptual system and move into a supersystem, essentially a more general system. And since language itself is the most general system of concepts, people with differing philosophical outlooks, for instance, who consequently adhere to different axioms, will never be able to agree on a universal theory that applies to everyone. This is because they are, in essence, speaking different languages, meaning they operate within their own most general systems of concepts. A truly universal common ground simply doesn't exist. Therefore, they can never truly reach a consensus, because at the heart of any worldview lie certain fundamental assumptions. These might be questions like, does God exist or not? Or, do parallel lines intersect or not? Or even, are Jews to blame for everything or not? These assumptions are chosen by individuals based on their personal inclinations, which are shaped by upbringing, alongside genetically predetermined predispositions and intelligence levels. Honestly, for any thinking person, Gödel's theory, brilliantly proven mathematically, doesn't really require further proof. It's quite self-evident. If we keep asking the same question over and over, for example, why, or what is that, within just 3 to 5 steps, we'll invariably hit upon the most general and therefore undefinable concepts. These are essentially very broad assumptions that are simply taken on faith. There are things that can only be accepted on faith, or understood purely through experience, and for which there's simply no other explanation. This is why different people hold different truths. Our understanding of the world is always subjective. After all, only subjects can think, not objects. And it depends on various random life factors, the books we happen to read or miss in childhood, our character, psychological type, birth traumas, and family influence. In essence, our worldview depends more on how we see, rather than on the world itself. That's quite a paradox, isn't it? Consequently, vastly different worlds are reflected in people's minds. In principle, people simply cannot agree with each other on everything. However, since we must coexist somehow, people are compelled to compromise and negotiate. And since absolute truth doesn't exist, there's no need to force it upon others, as if to enlighten the blind. Leading political thought in developed countries has arrived at a conclusion. If everything is relative, and whether one is right or wrong amounts to the same thing, then fighting for truth is pointless. Instead, let there be pluralism. Conversely, those individuals, political parties, and nations that haven't yet grasped this concept are, psychologically speaking, still operating at the level of medieval crusades, in humanity's romantic youth. And this is precisely why romantics are dangerous both in politics and in everyday life. By the way, the theory of relativity and Gödel's theorem aren't the only advancements in this area. Pluralism, incidentally, is a synonym for tolerance, and if you weren't aware, remember this. In any case, this word is going to be heard more and more frequently throughout the world. Great discoveries in physics, such as the principle of complementarity and Heisenberg's principle, have also contributed to this same understanding. Following the theory of relativity, quantum mechanics delivered yet another blow to common sense. When wave-particle duality was discovered, it wasn't just physicists who were scratching their heads. Philosophers were equally perplexed for a long time. It turned out that in the microworld, a particle behaves like a wave, and a wave behaves like a particle. Essentially, in the microworld, there are no distinct particles and no distinct waves. Instead, there are wave particles. You've heard about this so many times, and you learned it so long ago in school, that perhaps the true significance of this discovery has escaped you. But now truly reflect on it, and you might find yourself as utterly astonished as the philosophers were. Wave-particle duality, you see, blurred the line between an object and a process. An object is typically a material body. It usually has mass and occupies a specific point or volume in space. You can always point your finger at an object and say, there it is. A process, on the other hand, is movement. If the sun is an object, then its emission of electromagnetic waves is a process. A bicycle is an object, riding a bicycle is a process. Blood is an object, its circulation within the body is a process. A spring is an object, its oscillation is a wave process. A wave, in its purest form, is a process. Specifically, the oscillation of tiny particles within a medium through which the wave, in fact, travels. And in this sense, a wave, in a certain way, doesn't actually exist as a distinct entity. Molecules and masses of water in the sea move synchronously and rhythmically up and down, creating the illusion of water moving horizontally. In reality, however, the water particles themselves don't travel anywhere. They simply oscillate vertically in place. But because their movement is rhythmically coordinated, it appears as though masses of water are rushing from the sea towards the shore. I put "in reality" in quotation marks for a reason. We remember, don't we, that there is no single reality, and therefore waves do exist. You can consider them an appearance, or you can consider them a reality. As the saying goes, there's no accounting for taste. However, if you're professionally involved with processes, it's more convenient to consider waves as existing. After all, it's rather difficult to dismiss as non-existent a wave that can knock you off your feet, batter your legs with stones, and try to drag you out to sea. A process, fundamentally, is the movement of objects. So, naturally, an object is not a process, and a process is not an object. Everything seems clear enough. But then, in the micro world, it turns out that an object is a process, and a process is an object. An electron, for example, which is typically seen as an object, is simultaneously a wave, which is a process. How can we possibly make sense of this? An object, we might say, is matter, and a process is the movement of matter. This duality very clearly hinted to philosophers that matter and motion are intimately related. Indeed, matter can only exist through movement. And since movement requires space, it seems highly probable that matter, movement, and space are merely three manifestations, three aspects of one single underlying reality, much like the obverse, reverse, and edge of a single coin. But what exactly is this reality? Well, you can come up with a name for it yourself. After all, you're intelligent people, and once you get used to the name, an illusion of understanding will surely arise. Naming an object or a phenomenon is often the very first step towards understanding it. So, in short, this principle of combining the seemingly incompatible was termed the principle of complementarity in science. The principle of complementarity essentially means that a single reality can be described by two mutually exclusive theories, both of which yield correct results. The world, it turns out, is deeper than human logic. However, logic proved to be more cunning. For instance, sometimes we need to view light as an electromagnetic wave, while at other times we must consider it as particles, photons. This depends entirely on the experimental conditions and the specific outcome you're trying to achieve. The principle of complementarity isn't limited to physics, by the way. It applies across many scientific disciplines. In psychology, for example, you could employ Freud's model, which posited that all neuroses stem from repressed sexuality, and utilize classic psychoanalysis. Alternatively, you might opt for active analysis, or perhaps Gestalt analysis. You could also try Hubbard's Dianetics, or the regression method, or indeed something else entirely. Ultimately, it doesn't really matter which theory you use to explain human behavior. What truly matters is the outcome you aim to achieve. Because the main point of any psychological theory isn't just to explain why a person acts in a certain way, but to deliver a practical result, whether you succeeded in achieving positive progress with your client or not. Theories can indeed contradict one another. The key, however, is the result. If a theory yields results, then it can be considered correct or true, and that really just depends on your preferred terminology. Conversely, a theory that fails to produce any results is deemed erroneous. By the 20th century, scientists had come to understand that they weren't so much seekers of absolute truth, but rather creators of informational models. These models evolve, constantly becoming more refined, and yet they persist. For instance, the model of electromagnetism allowed us to light our homes with electric bulbs and ease labor with electric motors. The uncertainty principle was discovered by the German physicist Werner Heisenberg. This is why it's sometimes also referred to as Heisenberg's uncertainty principle. It is, arguably, one of humanity's greatest discoveries. Here's what it states. Delta X multiplied by delta P equals h bar. As you can see, it's a very simple formula to write. Simple like all truly brilliant ideas. Here, h bar represents Planck's constant. Delta x signifies the uncertainty in an elementary particle's position, and delta P denotes the uncertainty in the particle's momentum. The triangular symbol, delta, itself specifically indicates uncertainty. Uncertainty, at its core, is simply an unknown. In the most direct sense of the word, it's crucial to grasp this. Physicists have incorporated unknowns into the formulas that describe our world precisely because uncertainty is inherently woven into the fabric of our universe. Indeed, uncertainty is one of the fundamental principles by which the world is structured. Heisenberg's formula tells us that we cannot simultaneously know both a particle's exact position and its exact velocity. And remember, momentum is the product of velocity and mass. What we can do, however, is vary our ignorance, so to speak. We can choose whether it's more important for us to know the velocity or the position. Now, look closely at the formula. If we somehow pinpoint a particle's exact location in space, meaning the uncertainty of its position, delta x approaches zero. Then delta p, the uncertainty of its momentum, will, in that scenario, tend towards infinity. This is because their product is a constant value, Planck's constant. So, the first conclusion we can draw is this. In the microworld, there are no fixed trajectories along which particles travel, precisely because particles are smeared out across space. Formally speaking, the behavior of these particles is described by something called a wave function. The wave function indicates the probability of finding a particle at any given specific location. Essentially, the wave function describes not the particle itself, but a smeared-out probability distribution. We lack precise information about a particle not because we haven't studied it enough yet, but because that information simply isn't present within the very structure of matter itself. The particle itself doesn't know where it is or what it's doing. Consequently, in the microworld, nothing can be predicted in advance. We can only speak in terms of the probability of certain events occurring. The world, then, is built from these unpredictable particle bricks, and as such, the world itself is unpredictable, not fated, subject to randomness, and fundamentally probabilistic. So why, then, do physical laws exist? I mean, we have Newton's laws, Coulomb's law, the second law of thermodynamics, Ohm's law, the law of universal gravitation, and the laws of gas dynamics, just to name a few. Why are they followed consistently, not just occasionally? Where exactly is this unpredictability? Well, it's confined to the microworld. In the macroworld, however, the behavior of massive objects, composed of trillions upon trillions of particles, is quite predictable in simple interaction scenarios. Why is that, you might ask? It's because in the microworld, the probabilities of different events occurring vary greatly. The wave function tells us, for example, that the probability of finding a particle here rather than there might be 90%. Or, put another way, 90% of all particles will be found here, not there. This implies that a process involving a vast number of particles will proceed precisely in the direction that the majority of them are moving. These changes are directed and therefore irreversible. Irreversible processes create the illusion of the arrow of physical time, which, as we know, is irreversible. But time itself isn't what's irreversible. Naturally, time doesn't exist independently. What's irreversible are simply the physical processes that occur in space. For example, people age, the Egyptian pyramids crumble, and the sun will eventually burn out. Nevertheless, there still exists a non-zero probability that a kettle placed on the stove instead of boiling will freeze. The second law of thermodynamics is never violated. Heat always transfers from hotter bodies to colder ones. Although, theoretically, of course, all physical laws are statistical in nature, meaning they might for a split second not hold true. But you're more likely to win $100 billion in the lottery without even buying a ticket than a brick suddenly flying upwards instead of falling down? I actually considered simplifying that last phrase by leaving out "in simple cases of interaction." However, I decided against it, and here's why. Firstly, physical laws are ideal models that only work perfectly under ideal conditions. And secondly, in cases involving real, complex, multifactorial interactions of many bodies, fields, and phenomena, predicting anything becomes extremely difficult. Has anyone ever predicted the weather or oil prices with 100% accuracy?
Exactly. The world is not predetermined.
Complex systems, in other words, are not described by the simple equations we all, to varying degrees of success, learned in school. Instead, they're governed by nonlinear differential equations. Consequently, these systems behave in ways that are difficult, or even impossible to predict. Randomness in the microworld is unevenly distributed. Some things are more probable, others less so, and this means that most particles behave in a particular way rather than randomly. This, as we've already understood, is what allows physical laws to operate. That's why complex systems are difficult to predict. In some of these systems, under certain circumstances, a small impact can lead to significant results. If a system is in unstable equilibrium, much like a pencil balanced on its tip, any random nudge in one direction or another will push it out of equilibrium, and the situation will then develop in one specific direction. Similarly, if you aim a billiard ball at a sharp, angular object, then depending on tiny, random changes in its trajectory, the ball might, after impact, roll either left or right. The world, or rather individual unpredictable particles in complex systems, operate according to the laws of strange attractors. An attractor is an oscillating mathematical function. A strange attractor, then, is an oscillating function that exhibits unusual behavior. As it develops, an attractor enters a stable mode and begins to oscillate around an equilibrium point. However, at some unpredictable moment, for an unknown reason, it might suddenly sharply shift away and begin oscillating around an entirely different equilibrium point. These fly-off points are known as bifurcation points. A bifurcation point is essentially a point where randomness can propel a system far off its original course. Strange behavior, isn't it? And that's precisely why mathematicians named these functions strange attractors. Typical complex systems that behave like a strange attractor include the human body, an ecological community, and a social system. For example, imagine Napoleon appears, and a country's development suddenly shifts in a different direction. Or, consider a sudden random event, perhaps a nervous breakdown, that pushes a weakened organism out of equilibrium. It might then fall into a different state, leading to someone developing cancer. However, Napoleons and nervous breakdowns are only truly dangerous when systems are at a bifurcation point. This means they are oscillating in a state of unstable equilibrium, just awaiting the slightest push. For stable systems, however, neither nervous breakdowns nor even figures like Hitler pose a threat. It's simply not that easy to dislodge them from their potential. Well, so here's the answer to the question. Can a genius change history? Yes, they can, but only at a bifurcation point, when a country is at a crossroads. Now, regarding the term unstable equilibrium, it would actually be more accurate to say unstable non-equilibrium. And phrases like, a species is not in equilibrium with its environment at all, are frankly nonsensical ramblings. In fact, only the deceased are truly in equilibrium with their environment, and even then, only once they've fully decomposed. A living organism, on the other hand, constantly struggles against its environment every second. The environment tries to reduce the system to complete dissolution in accordance with the second law of thermodynamics, which states that in closed systems, entropy does not decrease. Entropy, as you may know, is a measure of chaos or disorganization. An organized living system, however, actively resists this entropic pressure from the environment. It struggles for its existence, acquiring energy that it draws from that very same environment, often by taking it from other living systems through competitive struggle. Therefore, when discussing living systems, it's more accurate to describe their normal modes as either stable non-equilibrium or unstable non-equilibrium. So, how can evolution possibly exist in a world where the second law of thermodynamics is constantly at play? This relentless second law, which increases entropy, seemingly destroys all existence, reducing it to a chaotic thermal jumble of molecules. After all, this is one of the fundamental laws of physics. It's no wonder that old Clausius spoke of the heat death of the universe. So why is it that all around us we see constant complexification instead of destruction and simplification? Could this be some form of divine providence? The second law of thermodynamics states that entropy in closed systems does not decrease. As you can see, this law applies only to closed systems. That is, systems that do not exchange energy with their surroundings. However, no truly closed systems exist in the real world. They exist only in the minds of physicists, much like the concept of an ideal gas. Processes of negentropy, of increasing complexity, occur in open systems. These systems possess sufficient diversity, and the second law, well, it doesn't really apply to them. Or, more precisely, it doesn't play a decisive role. If you continuously pump energy into a diverse system, this energy will inevitably trigger processes of self-organization within that system. This phenomenon was first noted in the mid-20th century by the Belgian physicist Ilya Prigogine, who specialized in non-equilibrium thermodynamics. He, in fact, laid the foundation for a new science concerning the organization of matter in open systems. Later this field was named synergetics, although Prigogine himself wasn't particularly fond of the term. Essentially, synergetics is the science of evolution. It's the study of how material structures become more complex within open systems. Virtually all systems in our world are open, with the possible exception of the universe itself. But whether it's closed or open, we can only speculate. We'll delve into that more precisely later on. For now, let's celebrate the great Prigogine, who, arguably, definitively closed the door on God in this universe. For a long time, the second law troubled philosophers. It seemed to present a clear contradiction to the increasing complexity we observe all around us. Homes are built, children are born, creative processes unfold, progressively distinguishing biocenosis and civilization from their environment. How could this be? After all, the second law seemingly demands only destruction and disorganization. Prigogine, however, explained how. He experimented with relatively simple physical systems, and even in these basic setups, he discovered that an influx of energy would alter the system's structure. Vortices would begin to form within it, consuming the incoming energy. But despite this structural complexification and the seeming violations of the second law of thermodynamics, overall is certainly not violated. If we consider the solar system a closed system, that is, if we disregard stellar radiation as an insignificant factor, then the entropy of the solar system is indeed increasing. The processes of creation here on Earth are paid for by the destruction of the sun. The sun is virtually our sole source of energy, apart from the tiny amounts we've learned to extract over the last half-century through the decay of transuranic elements mined from the Earth. Life on Earth is fundamentally paid for by destruction. This is a fundamental consequence of a fundamental physical law, the second law of thermodynamics. Just look around and you'll find thousands of real-life examples. A lion devours a gazelle, building its own body from the destruction of another's. Humanity conquers living space for itself. A caterpillar consumes a leaf, and all of us, collectively, are consuming our sun. Only 1/2 billionth of its energy reaches Earth, and that's enough to power all the processes here. Thanks a lot, by the way. Now, regarding this idea of complexification, let's recall an experiment conducted in the mid-20th century by Stanley Miller, who was attempting to confirm Oparin's hypothesis. Oh, right, you might not know who Oparin was yet. In the 1920s, the Russian biochemist Alexander Oparin proposed a theory that life on Earth originated in a primordial soup, essentially seawater teeming with organic molecules. He theorized that in the presence of methane, which at the time was believed to be the primary component of early Earth's atmosphere, continuous lightning strikes would cause organic molecules to react, forming increasingly complex molecules, and eventually, proteins. Miller decided to test this hypothesis experimentally, at least in its initial stages. He mixed methane, hydrogen, ammonia, and water in a flask, then heated the mixture and passed electric discharges through it. He didn't have millions of years at his disposal like evolution did. Within a few hours, amino acids had formed in the flask, and amino acids, by the way, are the building blocks of life. Proteins are made from them. Later, when it was discovered that our planet's early atmosphere was not, in fact, composed of methane, the initial excitement surrounding Miller's experiments somewhat subsided. To this day, Miller's experiment is cited in biology textbooks as an example of how life originated. But that's a shame, really. So, why exactly did the excitement die down? In essence, there should have been even more celebration. Miller's errors. Yes, the atmospheric composition Miller used, as is now believed, did not correspond to what actually existed on Earth at that time. But Miller succeeded anyway. So, you're saying life didn't originate in a methane atmosphere? Fine. Well, if you ever wanted it to, it certainly could have in a methane atmosphere too. Life, you see, is incredibly persistent. Overall then, even though Miller's experiment didn't perfectly match early Earth conditions, it remains a classic experiment confirming evolution. That is, the complexification of structures in a diverse environment when the system is saturated with energy. Now, we've strayed a little from quantum mechanics, haven't we? And yet, a rather important consequence flows from it. It can be formulated like this: by observing the world, we change it. Actually, scientists knew this even before quantum mechanics. If you connect an ammeter to an electrical circuit to measure the current, the needle won't show the current in the circuit you're investigating. Instead, it will show the current in that circuit with the ammeter attached. That's because an ammeter is an electrical device. It has its own resistance and therefore it alters the current. To minimize the distortion introduced by the instrument, engineers try to make the ammeter's resistance as low as possible. An ammeter, as everyone remembers, is connected in series. A voltmeter, however, is connected in parallel. For the same reason, to minimize distortion, its electrical resistance is, conversely, designed to be as high as possible, ideally infinite. We understand how electrical measuring instruments work. That's straightforward. But what about something like Columbus, merely observing America through a spyglass? How does he actually influence it? Or how does an invisible mouse affect the entire universe? Well, in the macroscopic world, the observer's influence on the object being studied is sometimes so weak that it practically plays no role at all. Especially if the object is vast and the observer is passive, as in our example with the mouse and the universe. However, in the micro world, the situation is entirely different. If you want to learn something about a particle, you simply have to receive a signal from it. You can get that signal, for example, using a quantum of light, which in physics is sometimes also referred to as a quantum of energy. But if the particle emits energy, its state changes dramatically. In effect, we gain information by killing or altering the very thing we wanted to learn about. This is because the information carrier is always material. This leads us to a crucial conclusion. Information is essentially matter structured in a very specific way. Think of it this way: black printer's ink arranged on the white background of a page in a particular order, or the specific magnetization pattern on a tape in a tape recorder, or an amplitude or frequency modulated radio wave. Do you see where I'm going with this? Information is material, exclaim the TV psychics and witches, with what they believe is profound insight. Thought is material, echo countless gurus. And they conclude, therefore it can influence the world. But they are mistaken. Thought is not material. The brain doesn't secrete thought in the same way that the gallbladder secretes bile. Such a primitive idea was only held by vulgar materialists, a view that was quite rightly criticized even by materialistic Marxist-Leninist philosophy itself. Thought cannot be isolated in a test tube, like urine or gastric juice. Since thought and information are not material, they are, in the truest sense, ideal. But here's the crucial distinction. Information is always matter, organized in a particular way. Can you grasp that distinction? If not, you will understand in a moment. Firstly, information always resides on some material carrier, without being that carrier itself. A book is not information, it is a thing, an object. The letters in a book are just ink. Secondly, these letters only transform into information when there is someone who can decode them into meaning. Information arises only when there is a perceiving subject. Norbert Wiener defined information as follows: matter organized in a certain way, plus a key for its interpretation. That, to be precise, is what information truly is. Information only truly comes into existence when there's an object, that is, matter carrying a message, and a subject equipped with the key to understand it. That key, of course, is knowledge and experience. So, in the micro world, a particle is dependent on the observer. That's because by simply observing it, by receiving those signal quanta, the observer inevitably interferes with the process itself. But even in the macroscopic world, the same principle often applies. This brings me back to the question of Columbus and his spyglass. Indeed, when we study the micro world, we change it directly. When we study the macroscopic world, however, we change it indirectly. And the mediator in this case is reason. Reason, you see, is an amplified capacity. It's the ability to acquire information from the world and then modify that world according to its own objectives. Evolution is a multifaceted process. We see an increase in the complexity of systems, their autonomy from the environment, and their capacity for reflection. What exactly are the human self, personality, reason, psyche, and soul? From a philosophical and practical point of view, these are merely reflections of the external world. Reflection exists across all scales. In the world of elementary particles, in solid bodies, in chemistry, in biology, and even in the social world. A photon, for instance, reflects off a mirror where the angle of incidence equals the angle of reflection. A heel leaves its reflection in clay as a pressed-in imprint. Complex DNA molecules duplicate by simply doubling themselves within a nutrient medium. An infusorian's reflection manifests as its ability to move towards light and then divide. As you can see, the complexity of this reflection grows as systems become more intricate. An animal reflects the world through its primitive psyche, which includes the capacity to remember and make predictions. Consider a wolf chasing a hare, cutting corners with anticipation. This is because a highly organized organism doesn't merely reflect reality, it can also predict it. This predictive ability allows an organism to successfully compete for resources against similar systems such as other wolves. And finally, reason emerges. Humanity's reflection of the world manifests as a highly complex psyche, while social reflection encompasses art, culture, and science. Now, for a rather unpleasant conclusion from quantum mechanical physics, the soul is not immortal. When the brain decomposes, the material structure upon which information about one's personality was encoded is lost. Consequently, the personality itself vanishes, it simply ceases to exist. How can that be? My friend Valera Chumakov protests. There are laws of conservation. According to them, nothing ever vanishes without a trace, it merely transforms into other forms and types of energy. Doesn't that mean myself is also immortal? It's true, the laws of conservation are indeed paramount in the physics of our world. However, physics, with its laws of conservation, applies only to the material world. Information, on the other hand, belongs to the realm of ideal categories. In the world of ideas, things can disappear and vanish completely, without a trace and, frankly, without pain. It's a pity, isn't it? But where does my soul go? People with restless spirits often ask, what about my thoughts, my experiences, after I die? Well, they go to the same place the hole in a donut goes once the donut has been eaten. Your unforgettable personality goes to the same place, just as the movement of a clock disappears once its spring unwinds completely. The movement of a clock and life itself are simply different forms of the movement of matter. Once that movement stops, well, that's the end of it. But what about movement? Chumakov persists. And energy doesn't simply vanish without a trace according to the law of conservation of energy. And that's also correct. Energy doesn't disappear. Instead, it degrades. Matter loses its order, and information dissipates. The energy from a stopped clock pendulum, or more accurately, its spring, has transferred into the slight warmth of the air and gears it heated, and your brain's activity, your very essence, relies on constant motion. Once in the grave, even the information stored there will vanish without a trace. Now, let's discuss how evolution makes its advances on the environment. It moves forward on a broad front, clearly indicating the direction of its main thrust. But if it encounters an obstacle, it simply bypasses it and pushes ahead. As you've probably gathered, this was a metaphor, but one very close to the heart of what's actually happening. The goal of this evolutionary offensive is to capture living space. In other words, expansion. The front of this advance is made up of soldiers, so to speak, similar elements. These could be individual people, viruses, organisms of a certain species, or even the species themselves. These soldiers, while similar, are not absolutely identical. Electrons, for example, are identical. You can't distinguish one electron from another. However, complex objects made up of many electrons are never completely identical. They always differ slightly. Ivanov might be handsome, while Petrov is, well, less so. They have different fingerprints, different nose lengths, facial features, ear shapes, varying heights, temperaments, hormonal system characteristics, natural predispositions, weights, hair patterns, blood types, and even shoe sizes. One might wear a size 39, while another wears a 45. All people are incredibly diverse. You won't find two who are exactly alike. Sometimes it's true women give birth to identical twins, genetic copies, but this is a rare exception. Moreover, people who interact with twins say that even these copies possess subtle micro-characteristics that allow them to be distinguished. Two banknotes, fresh off the printing press, one after the other, still bear their own unique micro-characteristics. And this isn't just true for people and banknotes. There are no two identical worms, buttercups, fish, or dogs. So, why does nature need deviations from the average? Why does evolution require this variation among individuals? Well, it's for the very same reason it needed death. Death emerged at the same time as life itself. Before that, there was no death. A stone, for example, is eternal, but a rabbit is mortal. Death is an inherent property of living subjects. Of course, a stone can also be destroyed, but that wouldn't be death in the biological sense. That's because death is not a random event, but rather a programmed destruction of an entity after a certain period. So, why was such a cunning mechanism as programmed demise necessary? Why didn't evolution simply create immortal, absolutely identical creatures that reproduce by division? The expansion of living space would proceed much faster that way. Yes, faster, certainly, but this would be an extensive path, a path of losing quality, a tactical win perhaps, but a strategic loss. In the long run, eternal, completely identical drones would lose out in expansion to the mortal and constantly evolving, and would soon be consumed. Anyone who fails to change and adapt to life's shifting conditions will inevitably lose. They are wiped out either by a changing environment, think global warming, cooling, shifts in humidity, or rising sea levels, or by competitors. Death, you see, allows evolution to quickly change the pieces on the board, one generation, then another, then a third. Sexual reproduction serves the same purpose. This dramatically increases diversity achieved by blending different traits from a father and a mother. It's a constant mosaic, further augmented by mutations. Mutations represent uncertainty in the living world, or, simply put, errors in molecular construction. The vast majority of gene mutations arise from the thermal movement of molecules. Only a small fraction occurs due to other reasons, radiation, or mutagenic substances ingested with food. Just one tiny error in the position of, say, a phosphorus atom in a long DNA molecule, one minuscule mistake, the probability of which always exists, such is the nature of the microscopic world, and we get an organism with a new morphological trait. Sound familiar? It's a strange attractor, a small disturbance leading to a significant change in an organism's fate. This is how, during reproduction, nature puts micro-level randomness to work on a macro scale. Death, sexual reproduction, and diversity are to cybernetics what the concept of set is to mathematics, one of its fundamental, undefinable concepts. The diversity of animal traits serves as a powerful tool for combating changing environmental conditions, a versatile toolkit, a constant process of finding the right keys to unlock survival. Today, certain forms are successful and in demand, but tomorrow, you might find that others, previously marginalized and in the minority, have become essential. Imagine, for example, a time when dinosaurs thrived, ruling the planet. Meanwhile, mammals, small and few in number, lingered somewhere in the background. But then conditions change, and in these new circumstances, large cold-blooded creatures like dinosaurs cannot survive. They die out, freeing up ecological niches for warm-blooded creatures who then conquer the planet. In such scenarios where the main attacking group is defeated, a reserve force surges forward flanking the obstacle. Diversity, in essence, is nature's battle reserve, ready for any eventuality. For the course of evolution not to halt during a crisis, the population must already contain those who were considered outsiders yesterday but today have become essential under the new conditions. Dictatorial and totalitarian regimes, you see, often have a limited historical longevity precisely because they suppress all dissent within themselves, which ultimately means they suppress diversity. When dictators speak of a united nation as a monolith that will crush all enemies, they do indeed transform their country into a monolith, one that is unparalleled certainly, but also inherently fragile. It's a well-known paradox that a strength can be the inverse of a weakness, and vice versa. In this context, fragility is the flip side of hardness. An absolutely rigid object, for instance, cannot truly exist. It would instantly shatter and break into tiny fragments because it is also absolutely brittle. For such an object to explode, the mere jostling of its own molecules, vibrating under thermal energy, would be enough. A rigid state system, with a nation unified around a single idea and a single leader, is perhaps only truly effective in times of war against similar systems. However, such a state has no prospects for peaceful development because it lacks flexibility. It's simply not plastic enough. A monolith cannot grow into the future. Instead, it is a flexible branch, soft and structurally more complex than stone, that can truly extend and thrive into the future. Societal diversity, by its very nature, is a product of tolerance towards others. This includes people with different skin colors, varying ways of thinking, diverse sexual preferences, different faiths, and, crucially, different ideas. The diversity of ideas, in fact, represents civilization's greatest wealth. And ideas, well, they are often the domain of the young. It is the young who drive progress. Consider the French mathematician Évariste Galois, who developed his theory of groups, a concept 100 years ahead of its time, when he was just 19. Lermontov was only 28 when he was killed in a duel, yet just look at the sheer volume of his complete works. Euler became an academic at the age of 20. Revolutionaries, you'll notice, are always young. Some people dream of immortality. Now, imagine a stagnant, self-satisfied, ambitionless community of eternal beings. The sex hormone testosterone would no longer surge through their blood, demanding decadence, zeal, heroic deeds, and the like. Each of them would have long ago accomplished everything in this life. And if any creative potential still remained, it would never be too late to express it, because, after all, eternity stretches ahead. What's the hurry? It is only death that truly compels us to hasten. We hear people say, "I'm already 40. What have I accomplished?" However, even if nature had created such a community of eternal beings, it would never have reached civilization. Having filled every ecological niche, these eternal beings would inevitably begin to devour their own offspring to eliminate competitors for those very niches. It is only our own mortality that forces us to care even slightly for our progeny, because that is the only way to extend ourselves into eternity. It's a rather imperfect method, one might say, but there's no other. The species' goal is to survive and project itself as far as possible into the future. And for this to happen effectively, it is better if individuals are both mortal and diverse. Now, diversity, interestingly enough, adheres to a specific principle known as the law of normal distribution. The name of the law itself is quite descriptive. It dictates how the characteristics of numerous similar objects are distributed. Take human height, for example. There are very few men who are exceptionally tall or exceptionally short. Most people have an average height or one close to it. The greater the deviation from the average, the smaller the number of such individuals, or, to put it another way, the lower the probability of finding someone with such a deviation. The intelligence quotient, or IQ, within a population is distributed along a similar curve. The average intelligence quotient for the human population is generally considered to be 100. Let's look at the results of one online IQ measurement. It showed that 1,352 people scored less than 75% shaft. Moving up, 2,370 people were in the 75 to 89 range. 4,413 fell between 90 and 96. The largest group, 5,136 people, scored between 97 and 103.6.5. Just slightly fewer, 4,941, were in the 104 to 110 bracket. 4,570, 4 people scored between 111 and 116 months. 16 months. 416 people were in the 117 to 122 range, followed by 3,225 in the 123 to 129 group. 2,480 people scored between 130 and 135, and 7,763 between 136 and 142. Finally, 1,515 people registered an IQ greater than 142. This Gaussian curve appears in many aspects of life. Artillery shells, for instance, land in a Gaussian distribution around the aiming point. The probability of detecting a particle at any point in space is also distributed according to a Gaussian curve. Essentially, Gauss's law is simply a reflection of the quantum wave function of the microworld in the macroworld. Blood pressure within a population is distributed according to Gauss's law. Even the size of ball bearings produced in factories follows a Gaussian distribution. In engineering, medicine, and other applied fields, 2 vertical lines are often drawn on a normal distribution graph, cutting off the extreme values of the curve. Ball bearings falling to the right or left of these lines are considered to be outside the sizes specified by the engineers. But drawing the line for what's considered normal? Well, that's where things get interesting. Can we consider a person with a height of 195 centimeters or an intelligence quotient of 143 to be abnormal? It really depends on your perspective, on how you define those boundaries. If you want 95% of the population to fall within the norm, then anything in the remaining 5% is an anomaly. In that case, both 195 centimeters and an IQ of 143 would indeed be considered abnormal. However, it's important to remember that both these values still lie on the normal distribution curve. So, normal and abnormal are really just matters of taste, a question of where you draw the lines. So, what are some of the implications of the law of normal distribution? Well, here's one example. Propaganda can never truly encompass all residents of a large country. There will always be people untouched by the information. Take Russia, for instance. You might think, who in Russia doesn't know Gagarin? Yet, public opinion polls show that there are people in society who don't know who Gagarin was. On the other side of the curve, you'll find people who know a great deal about Gagarin, but their numbers are also extremely small. We could even find someone who doesn't know that 2 times 2 equals 4. Such individuals exist, for instance, among those with severe intellectual disabilities. Or perhaps you no longer consider them people? Another reflection of the law of normal distribution is what I modestly call Nikhanov's law, my own personal law. It states that all significant dependencies exhibit an extreme or nonlinear character. Curves with a maximum or a minimum are referred to as extreme curves, and the peak or trough on such a curve is called an extremum. Let me illustrate this with an example. So, for instance, if you hear someone say something like, "The more you drink, the worse it is for your health," you should know that this statement is fundamentally flawed. This is because it assumes a direct proportional relationship, which frankly is an oversimplification of natural processes. A truly significant dependency, however, should resemble a Gaussian curve, meaning it has an extremum, a peak or a trough. A direct proportional relationship, on the other hand, can only hold true as a first approximation. Generally, people implicitly define similar boundaries for its application. But if one person steps outside that defined domain, then a disagreement naturally arises between them. If we expand the scope of alcohol consumption from 0 to infinity, we'll actually find that there's an optimal level of alcohol intake for health. Exceeding this optimal amount certainly causes harm. But surprisingly, consuming less than this amount can also be detrimental. This optimal intake, for example, is generally considered to be around 1 glass of red wine per day, which is roughly equivalent to a shot of vodka. Statistics actually show that individuals who consume about 1 glass of red wine daily tend to suffer less from cardiovascular diseases and generally live longer. Now, the statement, "the more you drink, the worse it is for your health," is clearly aimed at someone who might be overindulging in alcohol. It only holds true within the range to the right of that optimal point. If you were to plot a graph showing mortality rates versus the daily intake of pure alcohol, you'd see a curve resembling a Gaussian distribution, complete with a distinctive peak. The optimum, incidentally, is around 30 grams of pure alcohol per day. These significant extreme dependencies I'm discussing here are, in essence, simply reflections of the normal distribution curve. Take, for example, the common saying, "The more you exercise, the better." This, too, is a misconception. The relationship between health and exercise is, in fact, an extreme one. There's a particular optimal level of activity. Exceed this optimum, and you start facing overtraining and professional ailments, conditions common to all professionals, including athletes. Or how about the more powerful the engine, the better the car? Again, absolutely not. This dependency is also extreme. Beyond a certain point, increased engine power significantly degrades a car's handling. Only a few dozen people on Earth can effectively drive a Formula One car and actually derive enjoyment from it, rather than just stress. Indeed, if you were to equip a car with a rocket engine, instead of pleasure, you'd likely meet a rather swift demise. It's the same story when it comes to personal hygiene and the cleanliness of our homes. Up to a certain point, hygiene is certainly beneficial. It protects us from illnesses. But it really is only beneficial up to a certain point. Excessive cleanliness, ironically, can lead to various ailments, particularly allergies. For instance, in experiments with astronauts, when perfectly healthy individuals were placed in sterile environments, they began developing allergic reactions. Your immune system needs something to combat. When there's nothing for it to fight, it can, in a sense, start attacking anything at random. Statistics show that 38% of the world's adult population suffers from various allergies. This trend is particularly noticeable in developed countries generally, and in Japan specifically. In Japan, for example, people are literally obsessed with cleanliness and a fear of germs. They've even gone so far as to create individual, disposable, hygienic covers for computer mice. Ultimately, excessive cleanliness is only marginally better than outright dirt. I recall an experience from a Bedouin settlement in the Sahara. We were explicitly warned, do not drink the water consumed by the local inhabitants. A European stomach, being unaccustomed and perhaps a bit pampered, simply won't be able to cope with the local microbes found in untreated water. It's a similar situation with mental health. The more comfortable and affluent a country's living conditions, the higher its rates of mental illness, suicides, and depression. Conversely, during wartime, not only do rates of depression plummet, but people even seem less susceptible to common ailments like tonsillitis. In extreme situations, the human body mobilizes its resources. In comfortable ones, it tends to relax. So, one might jokingly ask, which would you prefer, war or a common cold? So, whenever someone tries to convince you of something by presenting a simple, direct, or inverse proportional relationship, it really doesn't matter which. Take a moment to pause and consider. More often than not, you'll discover that the function they're describing is actually an extreme one. Your real task, then, is to identify that optimal point, rather than simply succumbing to emotional appeals. Now, if you find yourself unable to visualize the function as having this humped or trough shape, it's one of two things. Either you've incorrectly defined the dependencies and their boundaries, or, quite simply, the function itself isn't truly significant.